Here's a few quick examples of simplifying using trig identities, simplifying algebraic expressions involving trig functions using trig identities. Here's number 6. The quantity secant phi, notice that's a phi, not theta. Theta, it's horizontal, and phi, it's slanted. Or it's almost vertical, but it's slanted. So secant phi minus 1 times the quantity secant, there's a c in there, secant phi plus 1. So all of our usual rules of algebra still apply. We can still multiply things out, FOIL it in other words, but we want to be on the lookout for special things about trig functions to be able to simplify. And usually the goal is, for most of these ones that you're going to do in the book, is you're going to be able to get it down to just one trig function. Maybe squared, maybe, we're not sure what trig function, but maybe even just a number. So let's just multiply that out. It's the difference of squares. So a minus ba plus b is a squared minus b squared. So it's secant squared phi minus 1. And as soon as you see that secant squared, we want to remember that we can use 1 plus tangent squared phi is equal to secant squared phi. Okay. So using this identity, if somebody just gave you secant squared and you went to this, that's actually a little more complicated because it's a 1 plus. But because you have secant squared minus 1, we can just plug that in there. Anytime you see a secant squared ever, if you want to, if it's appropriate, you can replace that with a 1 plus tangent squared phi. And that's about as simple as it's going to get. Tangent squared phi. It's one trig function squared. There's not much you can do with that. So that's going to be about the simplest version for that one. So we used ordinary algebra, and we used one of the Pythagorean identities, the tangent secant version of the Pythagorean identities. Now, let's go to number 10 for another example. Cosecant x over sine x minus cotangent x over tangent x. Okay. Well, notice in the first one, one thing back to the first one here, I didn't convert to cosine and sine. I went ahead and did some ordinary algebra first, and then as soon as I saw secant squared, I realized I can keep that in terms of secant and tangent, and I don't have to convert things to cosine and sine. Even though that's a strategy that you could use, it would be cumbersome. Here, I've got 4 different trig functions coming in, and so it's not a bad strategy to convert to cosine and sine. We can convert cosecant to 1 over sine, but that's going to make this kind of messy. And I think it's better to look at the structure of each of these fractions. Cosecant and sine are paired together because this cosecant is 1 over sine, and cotangent is 1 over tangent. And so that's suggesting I want to you do these on their own terms and do these on their own terms. And so can I get cosecant in terms of either sine or cosine? Well, if I get it in terms of sine, I'm going to be kind of privileging the thing on the bottom, and I'm going to end up with a fraction. And one of the things that's really a good goal is to try not to end up with fractions. That's why we have names for functions like cosecant, so that we don't have to write them as fractions. So what I can do is I can realize that that's cosecant x times 1 over sine x. Hey, that's cosecant itself. Minus cotangent x times 1 over tangent x. That's cotangent as well. Okay, so here I really am looking at it carefully and realizing that there's something special about this expression. And it's certainly not the only way to do it. The other thing is that if I have something minus something, I'd really like to get that into a Pythagorean identity form. And this is one of the forms of the Pythagorean identity, because here I've got cosecant and cotangent together, and that's something I want to recognize as relating to this one of the Pythagorean identities. And let's see. Oh, yeah, if I move the cosecant over, or let's see. Sorry, this is a minus now. I guess I'm moving the cotangent over and subtracting it and leaving the 1 on the other side. Sorry, let me do it that way. There we go. I just got confused. So 1 is cosecant squared minus cotangent. Oh, look, that actually secretly is just the number 1. Wow, that's pretty amazing. Okay, let me show you that real quick in a less sophisticated way, or less clever way, I guess, where I don't think about it as much ahead of time. It's definitely, I think that's the best way to do it that I showed you. But what if you just got stuck, and if you have to go back to a default strategy, namely put everything in terms of sine and cosine? Let's see how it would work out. Because I don't want to give you the impression that you have to see some clever key to the problem. But I also don't want to suggest that this is the best way to do the problem, what I'm going to do right now. But if you need to, if you get stuck, you can do this kind of thing. Whew, that looks kind of messy. But if we simplify the fractions, that's 1 over sine, and dividing by sine means times 1 over sine. So that's just 1 over sine squared. Then cosine or sine, let me do that one carefully. Cosine x over sine x times the flipped version. Okay. So that's 1 over sine squared x minus cosine squared x over sine squared x. Put it over a common denominator. So here I'm not using anything clever about trig functions. I've just used the basic definition of these 4 trig functions in terms of sine and cosine. And then I'm just using ordinary algebra and things that really are never, there's never judgment calls on these. If you have a compound fraction, you always simplify it and try to get into a single fraction. If you have adding or subtracting fractions, you always put it over a common denominator, and luckily it already is over a common denominator. Now, I do have to use the Pythagorean identity. Here, we use the fact that cosine squared plus sine squared equals 1, or in other words, 1 minus cosine squared equals sine squared. It's a really common form of the basic Pythagorean identity, that if you see 1 minus cosine squared, it's sine squared. If you see 1 minus sine squared, it's cosine squared. So this is now sine squared x over sine squared x. And we're done. Definitely the long way to do it, but there wasn't anything that where we had to be really clever. We just had to be patient and still be looking out for Pythagorean identity, but it was kind of a more basic one. Last one, number 20. Oh, very similar to what I just did, actually. 1 minus cosine squared theta over sine theta cosine theta. Again, it's a matter of recognizing this. So here, you really do have to be watching out for this. You might think, oh, if I'm just going to do sort of ordinary algebra that's not special to trig functions, I would like split it up. Maybe 1 over sine cosine minus cosine squared over sine cosine. Maybe do something like that. But you have to look out for this. 1 minus cosine squared should be a red flag. I know you guys are brand new at this, but it's definitely something you want to get used to. As saying, hey, you know, that's simpler than it looks. Okay. Now here, because it's a difference of two things, and cosine wasn't a common factor, I could not have canceled cosine here and cosine here. That's a very tempting thing to do. But it would be totally false. You can't cancel cosine with cosine here, because cosine is not a common factor. Here, there's no difference anymore. There's no sum or difference. This is just two sines over one sine. One of those guys cancels out. And sine theta over cosine theta, of course, tan theta. And so that's another one where we're looking out for that Pythagorean pattern. And so a lot of this, at least at this stage, is looking for those Pythagorean patterns, and otherwise just using your basic rules of ordinary algebra.